I'm like that. Today Chambers was like, Brandon, it's right there. And yeah, just being, I was like, I just wanted to see it.
Yeah, I didn't see how
no, but it's because it wasn't really like, it was more of the
hey, quiet now.
mental interaction.
So last time, did we get to the point where you had entered the acceleration in your calculator? So not yet. To do that, add this to your Y3. So you should have in Y1 and Y2 the other two formulas unless you deleted them. So enter the acceleration in Y3. And then you'll need to get this memorized. Acceleration is defined as the instantaneous rate of change of velocity. Mathematically, that means acceleration is equal to the derivative of the velocity, which can be written as dv dt or v prime of t. And that's all the same thing as the tangent slope of the velocity. So as you read this, you should see that it looks exactly like this. That's because position relates to velocity in exactly the same way that velocity relates to acceleration. Question? Cool. So that's how we're going to do here. We're going to jump over to the next sheet now that I just handed you. And start discussing this. So you've already got entered these three formulas now: position, velocity, and acceleration. And this is where the other handout I gave you becomes very helpful, the graph. So what Allison has here. So if we window 0 to 7, we'll see all of these now. So in your calculator, if you window 0 to 7, you see all of that. Have I showed this class the way to turn the equal sign on and off? No. We don't need it right now, but at some point in the future, you'll encounter a problem where you'd like to have all three of them in your calculator, but you don't necessarily want to see all three graphs. So to turn off a graph, all you have to do is highlight the equal sign, press Enter, and the calculator will unhighlight the equal sign, which will prevent that particular graph from being graphed. Question. So that's pretty handy in some situations. So I'll turn it back on, and then we'll window 0 to 7, zoom fit. And wait patiently for the graphing routine. And what we end up with is this picture, essentially. Although on the calculator, I'm starting at 0. In here, this one I start a little bit to the left of 0. So. Okay, next thing. So on the white sheet that you have, first question says, let's make this a little wider. It says, use the position graph to determine that the particle's position is decreasing from time equals 0 to time equal blank. On the calculator, the position graph is blue. And it's a little hard to tell what's happening in this region with the position graph, so I'd like to see better in this window. So I'm going to window from 0 to 1. Let's see what I get. Oh, wait a minute. Here's a case of where using the equal sign is helpful. it takes a while to graph all three. So if I want to save a little bit of time, the AP test is time, I can turn off the velocity and acceleration, like so, and then window 0 to 1, and it will only plot the position, since that's what I'm thinking about right now, zoom fit. So now I get a much more accurate picture of the position graph, and I can see that starting at time 0, position graph goes down immediately. So the position is decreasing starting at time 0, and now is when I would pick up this paper and say, like I'll just show it on the screen, right here. I'd say, okay, look, here's my position. And so position is actually decreasing from time 0 until I get to about here. Questions? Okay, I believe last time we showed how to find the minimum point right here on your calculator. New definition that you'll need to memorize. Okay, someone thought this was meant to be a classroom set. It is not. This is yours to keep forever. It's in the sheet protector so that you are reminded of the importance of the sheet. You'll want to get this thoroughly understood. The top portion of the sheet, you will have to memorize those ideas, not word for word, but you have to memorize the ideas. So this portion at the top has to be memorized, okay, not word for word, but the ideas must be memorized. The bottom half of the sheet is examples. So if this feels confusing and you're working a problem, you can look at one of these examples to help. I added the stuff in red. I would handwrite in that as well. Well, you don't have to. I'll explain in a minute. But the charts, if you look at it, this portion of the chart right here is just repeated right here. Like they're copies. You see that it's the same thing. So you can either draw what I've drawn or you can just use the shortened version. It will work either way. So anyway, back to here. This little feature on the position graph, this is known as a local or relative minimum. You look at your sheet protector reference, you will see at the very top it says right here, any function has a relative or local max, in this case min. The definitions are just opposite of each other. So any function has a relative or local min when that function changes, decreasing to increasing. So right here, the position function is changing from going down, decreasing, to increasing. So this is a local min. So if we find that local min's location, we have the answer to number 1. We will have determined that the particle's position is decreasing from time 0 to that time. Did I show you how to find the min on the calculator? So do that, go. So we would have had to change to 0 to 7 now, so you can see where that's located. That's right. Because the AP test requires 3 decimal answers, I would hit, I don't know if I showed you this stuff. Did I show you how to set up the calculator for 3 decimal? No. So go to mode and set right here to 3, and then the calculator will do all the rounding for you. So whenever you do a computation, it rounds automatically to the correct number for the AP test. Question? Awesome. Raise your hand if you're able to find this value here. Yes, who's got it? We get Tessa.
4.848.
So 4.848. Can you show me your hands again if you got that? Show me. 0.2 for Tessa. Okay. Do you need me to show anything? Next one. Okay, eyes up here. Look up. Okay, the purpose of this worksheet is to help you learn what this means. So basically, as you work your way down the sheet, it's just helping you see how position correlates to velocity, how velocity correlates to acceleration, okay, as you work your way down the sheet. So these two go together as we discuss. And then the graph, of course, is the picture of what we're discussing. So all those sheets fit together. So number one said, we found that the particle's position is decreasing from time 0 to 4.848. Question 2 goes with question 1. There's our combo idea. It says, use the velocity graph to determine that the particle's velocity is, here's what they're hinting at. If you look at the reference sheet, I've got a copy of it right here, you'll notice this says f prime, f double prime. Okay, that can be any function. The function we're working with is, we're calling this position. And then this would be the velocity, the derivative of the position. This would be the second derivative of position, also known as the acceleration, because it's the derivative of the velocity. And you need me to say that again, just wait. So we talked about it last time, no worries, we'll just review. So derivative, this is on your sheet from last time. So derivative means tangent slope. So if I find that, and this is the symbol for computing the derivative, this is another symbol for computing derivative. So if you find the derivative of some function, you are finding the tangent slope of that function. So what we talked about last time was this. It's a good question, Maya, 2 points. Okay, look up. If you follow the blue and you find this tangent slope, say it out loud, please. Is that tangent slope positive or negative? Negative. Negative. Whatever that negative value is, that becomes the corresponding y-coordinate on the velocity graph. That's how you make the velocity graph. You find the derivative of the position at that point. That's some negative number. That negative number becomes the velocity's value. So on the calculator, I can actually do the following. Let's go zoom fit here. Go to 7 now. Make sure we're all turned back on. Nope. Okay. Zoom fit. Wait patiently. Don't get a snack. I'm back. I should change the colors to match the other graph so it's easier to jump back and forth. I'll do that in a minute. So here's what I'm saying, Maya. Look, if we go trace and we get on the red, okay, the value of the velocity is 58.75. Because the derivative of position is the velocity, that means the tangent slope right here on the position graph, that tangent slope has a value of 58.75. That's what derivative means. Tangent slope, or instantaneous rate of change. All stated here on the previous sheet. Instantaneous rate of change. The only word I didn't put up was derivative, so apologize for that. Anybody else? Points for Maya? Okay, back to here. So when the position graph is decreasing, that means that you see the y-coordinates of the position graph going down. when those position graph y-coordinates are going down, you can be guaranteed that every value of the velocity will be negative. So every y-coordinate of the velocity. So look right here on the calculator. Here's the position graph. Notice, all along here, every single tangent slope that you would find on the position graph would have a negative value. That's why if you look at the velocity y-coordinates, every value of the velocity along that same path has a negative value. That's what the chart is telling you. So it's not a complicated relationship. It's quite simple, but the chart just summarizes it. Please, Heather.
So the chart's saying when the tangent slope is increasing, then the velocity is positive.
Not quite. Let me just say it back to you.
Okay.
It's saying, so this is representing position. So this is saying if I look at the position graph right here, and I see the position going down, so the y-coordinates of the position graph go down, I can be assured that during that same time frame, the y-coordinates of the velocity, which is the derivative of position, will all have negative values. So right here, when the position graph stops going down, that corresponds perfectly to this spot when the velocity stopped having negative y values. Is that better? Perfect. 2 points. Anybody else, please?
So like the I, D, and then like CU and CD, what are those on?
On the chart, and I'll refer to this as Danika's chart. It's on the wall over there. So the I indicates that whatever this function is, this could be any function. For our example, it's position. So this says if the position function is increasing, meaning that the y-coordinates of the position graph go up, then the y-coordinates of the derivative of position, the derivative of position being velocity, those velocity y-coordinates will be positive. The opposite is if the position is decreasing, the y-coordinates on velocity will be negative. This means concave up and concave down. We'll talk about those in a bit. So 2 points for Brennan. Did I answer your question?
Yeah.
Okay. Anybody else? Okay, so back to here. So use the velocity graph to determine that the particle's velocity is negative then. That's the correspondence. When the position is decreasing, the velocity has to be negative, and it has to be for the exact same time. So those two statements were placed side by side so that you can make sure you understood how they correlate. Allison, please.
So I don't know, like I'm not positive what I'm confused about. Like, how did you find where it's decreasing to 0?
On the position.
Yeah.
So what I did is I looked at the position graph, and I could see quite easily that all along here,
Yeah.
the y-coordinates of position are getting more and more negative. They're going down. So I know for certain that the position graph is decreasing through this region.
Yeah.
I was a little unsure here. Just it's so flat I can't tell. So that's when I enlarged my calculator view to see, oh yeah, it's still decreasing. So I can tell that starting at 0 and going all the way to this 4.848, the position is decreasing.
How did you find the 4.84?
Oh, gotcha. So that one, I went to my calculator and said, okay, let's find that low spot. So I went second, calculate menu, minimum. And I said left bound, lock that in, move to the right of where the minimum occurs.
Okay.
Is that what you
Yeah.
meant? Yeah. And that's where the 8.484 came from. So 4.848. Did that answer your question, Allison?
Yeah. thank
2
you.
points. Next thing. So here. So I put these both in red to emphasize that they really do go together. Okay, I did not have to calculate this value because I know that because of how position and velocity are related to each other, once I found this value, this has to be exactly the same. So there's no need to calculate it as well. On an AP test, they may ask you to use this graph to figure out where does the position stop decreasing. You would have to understand the correlation and find this value. Cool. Next thing. So number 3 goes along with number 1 and 2, so we'll circle that in red. Therefore, the particle's moving to the, we talked about this the other day, moving to the left. When the position is decreasing, the particle is moving left. Question. The position is decreasing, the particle is moving left. Please.
Like a real-world application, it wouldn't necessarily have to be left. It would just have to be like would it have to be left, or would it just be like moving backwards, kind of relative to the graph?
Oh, gotcha. For the simple type, I would have to be honest. I've studied more complex motion, but it has been quite a few years, so I don't have a good answer for you. Like for something that's moving in a complex fashion. But for the types of things we study, we'll only study motion that's either this way or this way. You could think of it as backwards if you want, instead of left, for sure. Because you could think of a car, like this is the origin, middle. And when I'm going forward, I have positive velocity. When I'm negative, I have backwards velocity. So you could think of it as forward and back. 2 points. Cool. Next one. Okay, question 4, I'm going to switch colors because we're now changing the general thought. The position is increasing from time what to time what? So I look at the graph, and pretty straightforward. Starting at 4.848, and then we'll just stop at 7. The position is increasing. So I make a note of that. So that's where the position is increasing. And similarly, if you look at Danika's chart, if the position graph is increasing, the derivative of the position graph must have y-coordinates that are positive. Please, pleasure.
Are you only putting the 7 there because that's how big our window is?
2 points. Outstanding. I just said that for our discussion, we'll go from 0 to 7. It doesn't mean that the graph doesn't keep going up. We're just only looking at that portion. 2 points. So this would be, therefore, the velocity is positive. You can use POS to represent positive. It's a valid abbreviation on the AP test. From 4.848 to 7.
Hey, I have a question.
Oh yeah, please.
So at 4.848, I thought that's when it's 0, like there's no like velocity.
Oh, I got you. So technically, we won't stress about 2 points. It's a good question. Won't worry about the tiny detail there for today, but you are right.
Okay.
Right at 4.848, the velocity is actually 0.
Okay.
Perfect. Anybody else? That's what you're referring to, Dan?
Yes.
Perfect. Okay, next thing. Slide this down a little bit. Okay, the A and B there I added, so you'll have to write those in. Sorry, it just occurred to me after I'd already made the copies. The x of t function, that's position, we discussed this just a moment ago, has a local min. So this is local or, oh, come on, buttons. It's local or relative min. At 4.848. Questions?
that's what a local or relative min is. What is a global minimum?
Outstanding, 2 points. So on the sheet protected reference, right here, Mikkel, this is the strict definition for relative or local. It's just what it says. Anytime the graph does this. Global means in whatever window we're looking at, what is the absolute lowest point? So it's possible, as is the case here, that this local min is also the global min. But you can have local mins that are not the global min. So if the graph were to do something like this, go along, have a local min, but then drop lower, this would still be a local min. This would be the global min.
Okay.
Is that what you meant?
Yeah.
It's awesome. Anybody else? Cool, keep going. So B says, the correspondence here is, if the position function has a local or relative min at this point, that also implies that the position function has a critical point. Let's show you what that means. So looking on your reference sheet, I guess I can make this a little bigger. I have to keep flipping back and forth. So right here it says at the bottom, any function has a critical point when the tangent slope of that function is 0 or undefined. So if we look at the position graph, right here, the tangent slope of position is 0. That means that is a critical point on the blue or position graph. Question? Oh, please.
Why would it be undefined? Like,
So if my position graph had done this, super Danny, okay, comes to a sharp point, there's no way to find the slope at that corner. So that's an undefined tangent slope.
okay, that makes sense.
That makes sense? Perfect. Anybody else? Cool. So that's what they meant by undefined. But that's still considered a local min, because if you look at the definition for local min, it says, does the function decrease and then increase? And it does.
Okay.
So anyway, this is a critical point on the position graph. So I wrote that here. So the x of t, the position function, has a critical point at 4.848. If you keep looking at the definition of critical point, it says any function has a critical point when the tangent slope of that function is 0 or undefined, or when that function's derivative has a y value of 0 or undefined. So statement, this 5b is telling us that exactly. The position function has a critical point at this time because the velocity graph is equal to 0 at that point. Those two things coincide. But the critical point is on the position graph. It's not on the velocity graph. It's on position. But you can find the critical point on the position by noting the value of the velocity. So these two line up perfectly again. You want me to say that again or differently or talk about anything related? Cool, next thing. Slide this out of the way. Okay, I'm going to erase this. Actually, we're going to make a copy. And then erase. So we can put this above. So starting at 6. The velocity is increasing from time equals 0 to time equal when. So I look back at my big sketch here. The velocity starting at 0, it's a little hard to tell what's happening. So I think I'm going to go to the calculator and enlarge that portion again. So let's go window. Let's change the colors. So the velocity is orange. Position is blue. Orange. acceleration is red. So let's change that. Good grief. Red. So now let's window 0 to maybe 1. Zoom to. That makes it pretty clear. The velocity goes up, then comes back down. So right here, I'd say the velocity is increasing from this time right there at the peak. Okay. So on the sheet, velocity is increasing from time 0 to time what? There's a correspondence here, though. Looking at Danika's chart. So this column, I'm using this for position. I'm using this column for velocity. Look up, though. You can just as easily call this column velocity, and then this column becomes acceleration. It's exactly the same relationship. So if the velocity is increasing, the y-coordinates of the acceleration must be positive. When the velocity is decreasing, the y-coordinates of the velocity's derivative, acceleration, must be negative. So you have two options available. You can either find where this local max of the velocity is occurring using the maximum on your calculator, or you can find where the acceleration changes from positive y-coordinates to negative y-coordinates. They occur in exactly the same place. You need me to explain that again. Cool. So go find that time. Go. If you haven't already. So. I'll just walk. Stop me if you have a question. Just grab the hot water. That would definitely find. So right in this one, that's going to tell us how small that is going to point to velocity acceleration.
There's like two correlations here.
Let me say that to the room. Two for Maya. Hey, look up 1 second. Hey, look up. So Maya asked a really good question. Looking at the graph, what you're confusing, no big deal, happens all the time. Velocity and speed are different. Very related, but not the same. So if I follow this portion of the velocity graph, the correct way to interpret what's happening is we say the velocity is decreasing because the velocity values are becoming more and more negative. However, Maya is correct. The particle's speeding up because the speed doesn't count for the negative value. So as the velocity goes to negative, this is 20, 40, 60, velocity is negative 20, now negative 40, almost negative 60. Yeah, the speed is definitely increasing, but the velocity itself is decreasing. So the portion of the graph we're looking at right now on question 6 is only concerned with this very early portion of the velocity curve where the velocity is actually going up. And conversely, the particle is actually slowing. Is that what you meant? It's perfect. Keep going. So find that point when the velocity stops increasing.
So the change right here.
Find where the velocity is local. So the calculate menu will do different computations on the graphs. So I can look and say, oh, I can find the maximum. That's one way. Another way is to note that we have here that when the velocity is increasing, the velocity derivative acceleration is positive. So you can also find where the red graph is equal to 0. That's the same as well. So I could go find the 0 on the red. But either way, it doesn't matter.
Yes, except it increases the slope is positive. Does that make sense? Yeah, you know the speed itself is cubic level. You're looking at the orange graph. Okay. Because you just made a mistake there. Yeah. The middle one? Yeah, the middle one. Wait.
I don't know why.
How did we find them? Test is so sweet.
Because, you know, at least we all got to suffer.
Did you figure it out? For just like the slides, for like, you just go right here, 2, so it's not very much. Like this is 1, so it's like really small.
It's going down.
Then it starts increasing, because it increases with that small. The slope is positive.
So the acceleration.
I don't know if that's
Oh, I know what you mean. It's like is it positive or negative? So from 0 to 0.202, what is this?
Thank you.
It's positive. So wait. So therefore the acceleration is positive from 0 to 0.202. But maybe it's probably decreasing, but it's still positive. Okay, but my question is the one that's more positive or decreasing? All be positive. Okay. So we were on
Hey, look out. So who has the correct answers for 6 and 7? Show me one. 2 points. We want to talk about them. Next thing. Okay, 8, 9, A and B. Not really anything new there. Just the same idea. So see if you can fill those out. Go. So So A and B you have to write in, but stop me if you have a question. Yeah. Let me see it back to you. Oh, don't think that either. Two more for Maya. If we look up, you're asking the right questions. Hey, you are asking the right questions. Okay. So again, you have to keep reminding yourself speed and velocity aren't the same. They're related. And what's happening, Maya, is because we're introducing the idea of negative velocity, which you probably haven't really studied in other classes, some of your intuition based on previous learning is getting fouled up. It's okay. Acceleration being negative doesn't mean the particle's slowing. Acceleration being positive doesn't mean the particle's speeding up either. We'll talk a little more why in the future, but just don't, for now, don't think that. So when I looked at the graph here, what you were thinking was good, but yeah, I have to not think that way. So right here, when the velocity is decreasing, we've mentioned that, kind of weird, but the speed's actually increasing. And during that same time frame, the acceleration is negative that entire time while the particle is speeding up. Because the reason is this: acceleration is the rate at which velocity changes. So I'll give you a really simple example. If my velocity is -1, am I moving left or right? Left. If, as I move to the left, I have an acceleration of -2, that means every time 1 second elapses, my velocity will become more negative. I will speed up.
That's very differently.
Very good. So back to here. So raise your hand if you have all of this filled out. Show me. Just another minute. So who has this filled out? Show me. Show me. Who's got this written down? So let's fill it out. So the velocity is decreasing from time equal 0.202. And what time do you have here, Rachel?
I haven't gotten that.
I haven't got that far. No worries. Alice, Ashley? Not yet? Hey, do you have this one?
3.298.
So how many have these two? Show me again. Point. Do we want to talk about it? Please. So when I look here, I see the velocity graph going down. until I get to about this location. That has to coincide perfectly with when the acceleration y coordinates stop having negative y coordinates and start having positive y coordinates. So I find this 0 right here on my calculator, and that turned out to be 3.29. Is that your question, Sarai?
Yeah.
Perfect. 2 points. Anybody else? Okay. Cool. Go here. Therefore, the acceleration must be negative for that same time frame. So there's nothing new to calculate there. It's just understanding the correspondence. So. The velocity function has a local or relative minimum at that point. Questions? Oh, please have it.
Is it a maximum?
Oh, let me see if this is what you're thinking. So the velocity will have a relative max here for sure. And then the velocity will have a relative min here. So really, on this sheet, either one would have been fine. This doesn't specify which one I'm referring to, so either way is fine. It's totally fine. Does that make sense? Because I didn't specify which one. 2 for Hadley. Anybody else? Please. Please keep asking. Okay, eyes on me. I'm very serious. Like, every time you ask, everyone else is like, oh, good. I wanted to ask that anyways. You ask really good questions, so don't stop.
For number 8, I found the minimum of the velocity graph and got like 3.4 because that's when it stops decreasing and starts.
Let's check your calculator. So your logic is right, the number's just not coming out correct. So that usually just means there's a small error here. Because the way you explained it was perfect. So yes, we're looking for when that velocity is at the bottom. So you asking is the perfect thing to do because your brain's saying, wait a minute, I can sound this difference. So show me on the graph how you can do that.
Can show it out one time.
We don't have to get it now. I should tease it quite a bit.
You know what?
Oh, I know. I know what's going on. Let me show you. I'm 99% sure this is what you did. Hey, eyes on the board. Okay, another really outstanding question, 2 for Maya. Here's what she's doing. All of you could easily have made the same mistake, so this is a really good one to fit into that category of, hey, right's as good as wrong, and better if we find out why. So she was thinking very, very logically that I want to find that minimum, so if I change my window to say 5, that will catch where the minimum occurs. So now we have to do the patient breathing exercises. Always very exciting. I'm tired of waiting. So I can press on and it'll stop, but I don't care because that's good enough. It'll stop. Never mind. Okay, here's what you did wrong. In fact, I want everyone to watch. If you can tell me the mistake, I'll pay you. So she goes second, calculate. She chooses minimum, because again, wrong's as good as right, so you need to know why. She finds the minimum. And then on your calculator, the screen's really condensed. I mean, it's black and white, so it's hard to see, right? They all kind of blend together. So I'm going to go, let's see. So I slid over here. Oops, got to get on the right graph. So get on the orange. So I'm going to push left bound. I'm going to move over a little bit. You don't say it out loud if you already know the mistake. I push right bound. I come back in the middle. I push enter. Okay, raise your hand if you know the error. Awesome. Hands up. Who can see what went wrong? So what is it?
You didn't go far enough to the left.
Correct. What the calculator did, and this is why you got two different answers, Maya. The calculator said, okay, you want me to find the minimum, so think of it this way. The calculator is not looking for the bottom. The calculator is looking for the minimum in the window, right? So she set the window over here just by accident, and the calculator found the minimum. Then when you did it again, different minimum. That's why. Does that make sense? Perfect. How many noticed that? 2 points. Well done. Really good question. That was really good. No, seriously, I was extra confused today. No. I would say you're not extra confused. You're just on track to do really well in calculus. Because you respond. I'm serious. You are responding exactly how you should. As soon as your brain says, wait a minute, something's not right here, you just speak up. And then we fix it and move on. If you never speak up, the amount of incorrect ideas just get worse and worse. And pretty soon, none of the connections make any sense. So just keep talking. It's perfect. I try really hard to be kind and gentle. If I'm not, please send some mean person to come tell me to be kind and gentle. So let's see, the velocity function has a critical point. At that time, 3.298. Now remember, the critical point is on the velocity graph. But this statement here is identifying the location of the velocity's critical point by looking at the velocity's derivative. Please, Allison.
For the local or relative, those things, do we just have to memorize or remember that it's gonna be that, or is there a reason?
Gotcha. I think I know that if I don't answer this, you just keep talking.
Okay.
Okay, all eyes here, look. So this is the definition of a relative max, and relative min is just the opposite. And that's just the definition.
Okay.
So you simply memorize that any function has a relative or local max. When the function changes increase to decrease, that's just the definitions. That answer it.
Yeah.
Keep going.
So on the top one, the critical point was
Up here,
yeah, on number 5 or whatever.
right here.
Yeah, the critical point was the lesser number, but then on the one down on the bottom, it's bigger number. Wait.
That doesn't matter.
That doesn't matter.
Let's look at the graph.
I did the.
Let's look here, Alice, and see if this will straighten it out. I'm going to give a bunch of examples. If you interact with me, I'll pay you several points. If I look at the velocity graph, right here, okay, and we figured out that that spot is 0.202. Just say it out loud, please. Is that a relative max or relative min of velocity? That's a relative max of velocity. That's also a critical point of velocity because it's a spot where the velocity's tangent slope is 0. Questions? That's also a spot where the acceleration value will equal 0 because acceleration is the derivative of velocity. If I come over here, this is a local min or max there. Min of what? Position, because this is the position graph. This is a critical point of what? Mistake, no big deal. Critical point of position. Because it's a spot, here's the definitions, look. Critical point is where the tangent slope of the function is 0. So I'm looking at the position, right here the tangent slope of position is 0, that's a critical point of position. But that's also exactly where the position's derivative will equal 0. I don't know if that helps straighten it out.
Yeah. Oh, so is it on the calculator we can do where it find this value?
We did use the calculator. It's like we can do it either way. We can find this spot using the minimum on the velocity, Or we can say, hey, it coincides perfectly with where the acceleration is 0. So
Yeah,
either way is
yeah.
fine.
Okay.
Cool. I've already marked down 4 points for helping me. So. It wasn't quite as interactive as I was hoping, but good enough. Other questions, please? No.
So it seems like you used the word derivative for relating the velocity to a different graph, but the way it's related is just the tangent slope.
Perfect. So I'll say it back to you. If it doesn't click, just keep talking. Blue is my position graph. If I go along the position graph, there's a whole bunch of points. I can stop at any point and find the derivative at that point. That value will become the y-coordinate of the velocity.
Okay. And then if you do that for the velocity, it becomes the acceleration?
Genius. 2 points. All because of the fact that that's what velocity and acceleration mean. So right here on your other sheet, velocity is the instantaneous rate of change of position, or the tangent slope of position, and that's what derivative means. Perfect. And then the same thing for, like you said, between velocity and acceleration.
So acceleration is instantaneous rate of change of velocity.
Perfect. Perfect. Acceleration is the instantaneous rate of change of velocity. Cool, next thing. All right, moving on. Okay, so, done those. Let's move this out of the way. Copy. Delete. Move this up. Okay, number 10. Okay, 10 and 11 are now talking about the relationship that deals with concavity. So let's talk about that a little bit. It actually should have put 11 first, probably. The velocity is concave blank from 0 to this point. So look at the large picture again. Here's velocity. Look at the shape of the curve. Say it out loud, please. Would you say that velocity curve is concave up or concave down? Down. Concave down. Pretty good. And the concavity will switch about in this vicinity. Everyone agree? Okay. I need to do a little interactive thing. Look right here and tell me, if I were to calculate the tangent slope right there, would that tangent slope have a positive or negative value? Say it. Positive. Good. If I move to the next point, like a little further along, I find another tangent slope. Would the next tangent slope be positive or negative?
Positive.
More or less?
Less.
Louder.
Less.
Good. So I had a tangent slope here that's positive. I move to a next tangent slope. It becomes still positive, but less positive. So if you're thinking of those slope values, is that an increase or a decrease? Louder? Decrease. Somewhat hesitant on that one. It's a decrease. You had a positive slope. The next slope became less positive. That's because the y-coordinates on the acceleration are the slopes of the velocity. The y-coordinates on the acceleration are the slopes of the velocity. You can see it. Right here, the slope of that curve is about 30. You move up, the slope here is about 20. The slope is decreasing. Okay, the word concave down literally means if you go point by point, the slopes will decrease. Look here. This tangent, positive or negative? Say it.
Negative.
Okay. Go to the next one. This tangent, positive or negative?
Negative.
More negative or less negative?
More negative.
More negative. Look at the correspondence. Right here, the tangent slope must be the y-coordinate of the acceleration. So it's about negative 10. When I slide over here, this tangent slope must be the y-coordinate of the acceleration, which is about negative 30-ish. So all the time that the velocity curve is concave down, you will see the y-coordinates of the acceleration decreasing. Danika's chart confirms that. If this is velocity, Remember, f isn't anything special. F's just whatever function you declare f to be. This is just the derivative of that function. So if this is velocity and this is acceleration, wherever you see the velocity curve being concave down, you will find the y-coordinates of the acceleration curve decreasing. We need me to talk through that again. Perfect. So back here, your calculator won't find where the concavity switch is. It doesn't have a computation for that. But you can find it. You can find where the acceleration switched from decreasing to increasing. Please.
So when it switches from concave down.
So pause for just 1 second. You're doing great. I just got to make a point here. Mark down 5. 5. Yeah, please. 5. Put 6. Okay. 7. Okay. I've already talked about how cancel causes all kinds of problems. It just like leads to mistakes. Don't cancel, right? Don't use this word either. It's also highly offensive. And Danny didn't know that, but he did make the offensive reference, so it's okay. I just use it too. You can use the word in certain places, and it's not offensive at all. I hope nobody's offended by this. Like, it's not offensive to say that hell is the place where the devil lives. It's, well, you know, whatever. You know what I mean? Everybody okay with that? Okay. That's not like, that's okay to say that, right? You know, and don't be offended, but you know, in certain literary texts, like famous books, they refer to a small donkey as an ass, right? That's okay. There's nothing. I'm not offending anyone, right? No one's blushing, so okay, good. So this is the same thing. Okay. In some references, it's okay to say the word it, but where you don't ever want to use the word it is when you start talking about different graphs, because on the AP test, if you use this word, they won't give you any points. Yeah, I'm serious. Like, they'll go, I don't know which graph you're talking about. So always say, hey, position, velocity, acceleration. So go ahead, please.
Okay, so
it's awesome. Good work.
On the velocity graph, so it's concave down.
Oh, don't say it again. Say velocity is concave down.
The velocity is concave.
It's hard. You have to work at it.
Velocity.
See, it right there is okay. I'll shut up now. Okay, good. Velocity is concave down. Yes.
Yes, and then the velocity graph switches to concave up as soon as the tangent slope, which is the acceleration, starts curving upwards, correct?
Perfect.
Okay.
Perfect, perfect, perfect. Perfect. And Danika's chart isn't anything magical, but it does summarize that nicely. Okay. And that's why it's on the wall, because it's just a really nice summary. Please, Allison.
So to find the number like 10, where it says the acceleration, it would be negative, right?
Actually, decreasing is the word we want.
Decreasing. But to find where it is decreasing from, do we find the minimum of the velocity graph?
Let me say it back to you. So the correspondence we're looking at is right here. If my velocity is concave down, the y-coordinates of the velocity's derivative must decrease. So that means acceleration must go down. It doesn't have anything to, it's nothing to do with negative. Acceleration goes down. Because if you look here, you'll see these acceleration values are positive and they're going down. These acceleration values are negative and they're going down. Yeah. All I care is that they're going down. So I'm looking for the min here on the red.
Oh, on the red.
That will tell me where the velocity switches concavity.
Okay.
And that's known as an inflection point, right here. Any function has an inflection point when that function changes concavity.
Okay.
Have you heard the word inflection point before? Nod. Excellent. Hadley's good. I don't care about the rest. Okay. All right. I'm just joking. No, I'm giving you a compliment. Oh, you're good. You nodded. Nobody else nodded. So like, oh, Hadley knows. What I don't care about the rest. As long as you know, I'm happy. Sorry if it didn't work very well. I feel bad. Are we good? I'll tell Chuck you didn't have to breathe and apologize again. You're very patient. All right. So what's the time there? Somebody find it? Anybody find the time?
0.75? Is that right?
Always do 3 decimals.
That's all I can do.
Yeah, I do respect that.
So the velocity is concave down from t equals 0 to that time. Again, it's showing the correspondence between the velocity and the acceleration. Question? Please, no.
So on the AP test, if it just gives you like 2 decimal places, or I guess for your answer, do you want us to add the 0?
Here's what I would have done, honestly. That doesn't happen very often, but this is what I would have done. If I were finding that min, once I found that it said 1.75, it would make me nervous. So I would probably change my mode just quickly. Just put it like an extra decimal. A few extra, just to make sure. I don't know. Stop. Float should work. Well, I don't know if trust float either. Just go 9. And then I'd find it again. 2 points for Noah. So we got to go left bound. I don't like driving. I'm just going to tell it that the left band's over here at 0. And the right bound's over here at 1, 2, 3. Yes is in the middle, 2. So now I can see that really, if I round to 3 decimals, since this is 9, I have to count up 1, so this becomes 750.
Okay.
That's why I know.
See what the 0.
Anybody else? Awesome. Way back to here. Okay. So these two went together. 12. 12 is moving on to a different section of the graph. So they're relating the concavity of the velocity to the acceleration again. So the acceleration is increasing from time equal 1.75 and the acceleration just increases all the way to 7, which tells me that the velocity must be concave up for that same interval. Question? Please, Lindsay.
For all the graphs that we're going to be doing, are we just going to go up to the maximum number that we're using, like 7 for this one? Or do you want us to say infinity?
Gotcha. No, for AP questions, they usually give you a window. So we'll just use that window 0 to 7. We may encounter some in the future that don't have any endpoints, but for now, the window's a little easier to understand. Perfect. 2 points. Anybody else? Okay, so then the same thing here on A. The velocity, v of t, has a critical point at time equal 1.750. Oh, my bad. Sorry, erase that. Inflection point. Because we're talking about concavity now. So this should say inflection point. Hint, it said and. At 1.750, because the velocity changes concave down to concave up at that point. These are also valid abbreviations on the AP test. So. Question? Awesome. Okay, don't lose this. We didn't get as far as I basically hand out more than you need. That's very common for me. Then we have a really, really good discussion. I'm paying really close attention to hopefully see if you're following, so I know whether to go faster or slower. We didn't get to this, that's okay. the homework is to finish the white. Okay? So you've got this side that needs finishing, and then the other side. So the back goes 18 to 40. Now on the back, don't leave, the bells are ring. Listen, hey, there are 3 new curves. Look, on the back it's 3 new position, velocity, acceleration. But it all ties together because it's also the back of this. And I will post the answers to that white sheet on my website, so they can give them to you.
What about one that ABC?
Don't worry about the ABCD. Good job, you guys. That's what I thought too. That's why I thought it was a little bit.
I'm calling from down to the main office. Blake Williams.
Oh, maybe
Carol Castle. Alina Harris. Jennifer Erickson. Morgan
I do think you'll like it. Oh yeah, thank you.